Let's look at this kick scooter. The speed limit on the section of the road is 80 km per hour. If the traffic police want to know whether the driver is speeding, how should we calculate it? We have studied physics in junior high school. Speed equals distance divided by time. We click the stopwatch, take a picture at the beginning, and take another picture 10 seconds later. Divide the distance difference by the time lag it takes, and we can know the average speed consumed by the scooter on the section of the road. But this is not accurate enough. The speed limit sign hopes that vehicle won't exceed the speed limit at any time. If it starts slowly at first, but in the second half of the journey he drag racing, although its average speed is not speeding, in terms of instantaneous speed, his scooter is still speeding. How can we measure the instantaneous velocity? This instantaneous seems to mean that we can only take one picture if the exposure time is extremely short. What we get at that moment is a picture of a scooter with no motion blur, and we can't even tell whether it's moving. In fact, instantaneous velocity cannot be measured. It can only be calculated based on the calculation method of average speed. The shorter the time span is, the closer it is to the concept of instantaneous. Let's have a look and examine the chart again. Assuming that the scooter starts with a constant acceleration and the relationship between distance and time is s equals 1.5 times t squared, with time as the horizontal axis and the distance as the vertical axis. So we can draw such a distance and time diagram, and the average speed just measured is to find the 2 points on this map. Connect them and measure the slope of the line. That is, the value of the horizontal axis divided the value of the vertical axis. But no matter what we do, the result is the average speed. How can we know the instantaneous speed? Let's carefully think it over. What instantaneous speed is? The word instantaneous means that there is no time interval. That is, the time interval approaches zero. If we want to know the instantaneous speed of the scooter in the 5th second, we can divide the distance difference between the 5th second and the 6th second by the time difference, calculate the average speed, and then estimate it. In order to get a more accurate result, we need to narrow the selected time interval. Okay, now let's try to find out what the instantaneous speed of the scooter is in the 5th second. I can drag the second point to narrow the distance between the 2 points and bring the speed closer to the instantaneous speed. The picture is so small that we can't see it clearly. Let me enlarge the coordinate system a little bit and a little bit, so I can continue to drag this point more precisely. Alright, now we will find that we keep zooming in. This process can be repeated all the time. If we use mathematical language to express what I just did, it is like this. Limit is the abbreviation of limit. When delta t approaches zero, this formula is a rigorous definition of instantaneous velocity at a given moment. We can also express the delta s in the numerator as a function of delta t. F 5 plus delta t represents the distance at 5 plus delta t, and f5 represents the distance at the 5th second. If the two are subtracted, we get their difference, which is delta s. The two can be further expanded. According to s equals 1.5 t squared, which are 1.5 times 5 plus delta t squared, and 1.5 times 5 squared respectively, after which the numerator becomes long. Let's simplify it a little bit, and it's 3 times 5 delta t plus 1.5 delta t squared. Then the delta t in the numerator and denominator can be reduced. This formula becomes 15 plus 1.5 delta t. Because delta t approaches 0, 1.5 delta t also approaches 0. In this way, we calculate the instantaneous speed of the 5th second, which is 15. But what if we want to calculate the instantaneous velocity at any time, such as t? What should we do? We just need to replace the previous 5 with t. We can calculate the instantaneous velocity at t second. This function about t is the derivative function. This calculation process is to use the definition method to get the derivative. The derivative of any simple function can be obtained by the definition method. For example, the derivative of fx equals reciprocal of x can be obtained in this way. Bring the function into the formula and establish a common denominator, reduce h, and the result approaches to -1 over x squared. We use f prime x to represent derivatives. More other function can be derived in a similar way. Do we need to rederive this formula every time when we use it? No. When you do your homework, you have to keep in mind these basic elementary function derivative formulas. But what if we face this derivative? We can also use the definition method to evaluate it. But the process is a bit tedious. We have an easy way. Introduce the median value u. We can split the formula into this form. The relationship between x and u is x squared plus 1. The relationship between u and y is y equals reciprocal of u. Our goal is to find out how much a small change in x will change y. In other words, how will the influence of delta x be passed onto delta y? And the derivative is the limit of the ratio of delta y to delta x. The first step, delta x to delta u, is easy. Let's look at the chart of this function. According to the definition just now, delta u is approximately equal to delta x times slope of this point. That is, the derivative of x squared plus 1, 2x. Let's first use p prime to represent it. The second step, from delta u to delta y, is for the same reason. If we look at the picture, we can see that delta y is about delta u times the slope of this point. In this particular case, the slope is negative reciprocal u squared. We also use y prime for the time being. After preparatory work, we now begin to look for the impact of delta y on delta x. Because delta u is affected by delta x, we can express the delta u of these steps as delta x of the previous steps. That is, delta y is approximately equal to y prime times u prime times delta x. Now, let me move delta x to the left of the equation, and we get that delta y divided by delta x is approximately equal to u prime times y prime. If the delta x approaches 0, then it means that the derivative function is u prime times y prime. Multiply the derivatives of these two simple functions. In this specific example, u prime is 2x. Y prime is 1 over square of u. Let me replace u with x squared plus 1. Then the derivative of the whole function is equal to x squared plus 1 parentheses 1 over square of them times negative 2x. This is the same as the result we calculate using the definition method. We just got the derivative of the complex function step by step. This method is called the chain rule. Although our above proof is not as rigorous as the textbook proof, we can already feel how the inferences passed from x to y. Of course, there's a simple way to write the chain rule. We can also abbreviate the left side of the formula to dy divided by dx, which means when delta x approaches 0, delta y divided by delta x, while the u prime on the right of the formula is du divided by dx, y prime is dy divided by du. This way of writing is easy to remember. Du looks like fraction has been reduced. In the following content, I will use this form to express the chain rule. Chain rule can also be extended infinitely. We can try to combine these functions in the upper right corner to see how the influences is passed. Indeed, this interaction is a bit strange. It shows the process of passing a small change in the function from the bottom to the top. Each time it is transferred from the x-axis to the y-axis. Delta y is approximately equal to the derivative value, the slope, of the current point multiplied by delta x. So delta y of the top layer is multiplied by the derivative values of the first 3 layers, and then multiplied by delta x. So the chain rule is the multiplication of the derivative values of several simple functions. This reminds me of the Thomas Stearns Eliot's words. What we call the beginning is often the end, and to make an end is to make a beginning. The end is where we start from. What we are talking about here is only a small part of derivative knowledge that will be used in gradient descent. Only when we understand the principle can we make the better use of the knowledge. That's the end of today's math video. See you next week.